All right, good morning. My name is Antti Romppanen. I'm coming from Nokia, where I'm heading the product management for data center infrastructure. The next topic is a bit different topic. It's about edge cloud solutions. While we all appreciate designs in open compute, like for example OpenRAC, they don't necessarily fit to all the use cases that we have in the telecom space. I'll be giving an overview about edge cloud solutions, why we need those, what does it offer, and then after that you will hear more detailed presentations about the proposed contributions and specifications that we have in that arena. Nokia is actually a platinum member in Open Compute. We are an official OCP solution provider, and today we are shipping OpenRAC-based solutions to customers worldwide, basically in all the continents, including US, Europe, India, Latin America, Asia Pacific, Japan. So you could say that the OpenRAC starts to be very well adopted for various operator use cases. Those include the typically core use cases that require a lot of capacity, a lot of density, ease of operations, energy efficiency, all the nice benefits that are there in OpenRAC. But when it comes to some of the more challenging workloads that need to be distributed in the network, we see need for alternative designs, additional designs. So if we characterize a little bit the requirements of the different services in the network, so starting from the basic services like browsing, looking at Facebook, email, you don't see so much of a requirement for low latency. You can actually use the service rather fluently, even though there's a 1 second delay in the network, as long as you have adequate bandwidth. But the more we are moving from the left bottom corner of this wall quadrant to the top right corner of this quadrant, where we see that the latency requirements of the services start to be in the range of less than 10 millisecond, even 1 millisecond level or lower. Bandwidth requirements start to be very high. So we see that actually traditional models for building data centers in the network are not enough. If we consider things like virtual reality, where we are streaming content over the network, if the delay in the network or latency in the network is too high, people start to actually feel sick when they are using the service. They are suffering from motion sickness. If we think about autonomous driving or even cloud-assisted driving, but autonomous driving as the ultimate use case, we all understand that the latency requirements in that kind of a service are pretty critical. When we are not so much latency constrained, we can actually build large data centers. We can centralize, and that is always good for efficiency. We get scale. But the more we move towards low latency, we need to build edge clouds, and there are actually various implementation models for those, and we'll look those in the next slides. 5G is going to be a big thing in our industry. It's already starting to happen in some of our markets, and that is actually enhancing the network architecture so that we are getting the low latency in terms of the network itself. But 5G doesn't basically solve the challenges which are related to the content itself. So if the content is not closer to the end users, if the content is not at the reach of this low latency, 5G is just a network architecture. So in that sense, with 5G, we are improving the access. We are getting less than 1 millisecond latency from the network. But at the same time, we need to move the content closer to the end users. Actually, the edge cloud is not driven only by mobile networks. We see very much requirements coming also from the fixed side of things. So at the top right corner, we see fixed access network transformation. Things like virtualizing broadband IP access, software-defined access network, virtualizing cable access. They require also highly distributed cloud capabilities. There's a lot of new use cases coming from the multi-access edge compute. So things like Industry 4.0, automating factories, automating mines, automating airports, transportation, and providing, for example, machine learning and AI-assisted services for those verticals again, we are talking about very much localized services, so requiring edge cloud capabilities. Then at the bottom right corner, you see actually that for the telecom, for the operators, actually this access to low latency access is something that is quite a unique asset. If we are able to utilize that asset to the maximum extent, if we are able to build flexible cloud capacity, offering millisecond level access to the services, we can definitely generate additional value with OTT players, with all the different kind of content providers, and increase the overall value that we have in the market. So all of these requirements are actually culminating in the architecture or reference architecture for the networks that we have. This is something that is stemming from the research work that Nokia has done within the Bell Labs research function. And here we are actually splitting the network into different tiers or different topology layers that are providing different levels of service. On the rightmost side, we have the central data centers. Those are the ones that run core functions in the network, OSS, BSS type of functions, operator, enterprise IT functions. There we want to build for scale. There we don't need so many data centers per country or per geography. And we can utilize, for example, OpenRAC version 2 based technology very, very efficiently. Then when we are moving more towards the access, starting to talk about regional data centers, aggregated edge data centers, we start to see already much more limitations in terms of physical footprint in the data center, in terms of power that is available, and therefore we need to have additional options for deployment. So we are talking about smaller OpenRAC-based systems for data centers where you cannot necessarily have 20 kilowatts of power per cabinet. We are talking about even smaller form factors, like you see there for the aggregated edge, the small box there, which is the open edge design that we have been starting to look into in the telco working group. Then there's a topic called far edge, which is taking the cloud actually very close to the actual radio. We are talking about definitely CO level deployments, but even radio side deployments. And there can be hundreds, thousands, tens of thousands of small clouds like this in the network. You don't necessarily have a huge amount of compute in those sites. It might be just a few servers here and there. But when you count the number of sites times the number of servers in those environments, you can understand that actually going forward, there will be as much compute here as there is in the big central data centers in the network. The requirements for this environment are tough, so it needs to be very compact. It needs to be very low maintenance, so highly automated. You don't want to go to hundreds or thousands of sites often to update firmware or things like that. It needs to be very energy efficient because you might only have like 2 kilowatts of power available in those sites. The challenge in those highly distributed sites is that there's no space for traditional data center hardware. You don't have the physical room for that. You might be only able to fit 600 millimeter deep cabinets. Cabinets might need to be next to a wall. So doing hot aisle, cold aisle separation like in a larger data center is quite a challenge. Classical data center hardware is not designed for that. And that is why we are right now working on the Open Edge project and already have been proposing some of the initial designs how to actually solve all this. So what we need is really a compact data center solution that is able to fit basically everywhere where we are building, for example, base stations today. The Open Edge design that has been proposed by Nokia is something that is reusing very much industry standard base station dimensions and characteristics. We understand that sometimes this may be even installed even on a pole, in an outdoor cabinet somewhere in the middle of nowhere, on a rooftop, on the street side. And this means that for example, base station type of a design is very good for that. But still keeping all the benefits that are out there in open compute. So we need to have toolless operability. We want to have it fully front operated, very much optimized for power efficiency, and all open. So that's what we want to actually aim for. And right now in the Nokia booth in the hall, we actually have a open edge data center solution running in an outdoor cabinet, which can be deployed on a pole even if you so like. And that is showing that it's possible to make the designs utilizing still fully OCP principles, but making it much more compact and lightweight. One of the challenges in those highly distributed edge sites is that we still need quite a lot of power for the processing, despite the restrictions that we have on the sites. One of the things that how we can actually get more beef out of the edge data centers is by using hardware acceleration. So some of the examples here are showing that when we are, for example, using GPUs for content acceleration, we can get multiple times more performance out of the edge data center. Of course, it means that the particular data center is not anymore so versatile, so all multi-purpose after it has this kind of a specific silicon there. But the underlying design needs to be able to accommodate various use cases. And that's why, for example, adding GPU acceleration, adding FPGA acceleration, adding for example, quick assist-based acceleration for encryption or things like that, or Nokia ReefShark for some of the base station acceleration. All of those use cases need to be possible. I mentioned that the data centers need to be very low touch. So this is not just a challenge for the hardware engineers. It's also much more a solution level challenge, that how do we maintain the hardware in all of those distributed data centers with minimal effort. Also for that, we should utilize open solutions, open interfaces, so things like Redfish-based interfaces for managing the hardware, Ansible-based automation to do all the necessary hardware operations, and so that we are able to manage that from central management, so that we can actually handle all these distributed data centers from a single pane of glass, or through a single pane of glass. Actually here is an example that it can be achieved. So with this kind of open management software, we can actually automate the hardware deployment and management to a great extent. Here we are showing a proof of concept or trial here in Europe, where we were deploying OpenRack using this kind of automation. And we were happy to see that we can actually shorten the deployment time for hardware from what used to be like 2 days in the past, can be now achieved with the automation in less than 30 minutes. And with much less manual steps, much less errors. And this is the type of a zero-touch maintenance that we need to actually do also for the edge cloud. So starting from the moment that the rack actually, or cabinet actually arrives to the site, you are opening the wooden crate, connecting the rack. Then you start allocating management IPs, you start checking the inventory on that, updating firmware. All of that needs to be automated and run in a very short time without issues. And then we multiply this by potentially thousands of sites. Some of the use cases that are requiring the edge cloud deployment are, for example, Cloud RAN, very important use case, for example, for Nokia and for operators. We see that cloud actually brings a lot of flexibility also for the radio access network, and eventually utilizing virtualization for different layers of the access. So starting from the non-real-time parts of the radio, but going all the way to the layer 1 real-time processing, virtualizing that, we can actually move from a proprietary architecture in the radio to a much more open architecture, supporting open hardware and also open interfaces. So with that, we are, in the end, finally, the only sort of a physical part of the radio access eventually would be the antennas that are out there. Everything else can run in the cloud. Of course, it's not something that happens in overnight, so it's very much a transition and different markets moving in different phases. And the type of deployment models are varying, for example, based on the capabilities for the transport in that particular country. In our AirScale Cloud RAN solution, we can actually flexibly build more central capacity for the workloads, and then deploy in the edge cloud things like virtualized base station, multi-access edge compute running on the open edge environment. As said, there are multiple different kind of approaches on what works in which market. So where we, for example, will build this bit more centralized so that there's actually a real data center running the radio, or where the radio will be virtualized radio functions will be deployed even very close to the antennas, even at the rooftop if needed. Another important use case here is virtualized EPC. So virtualized EPC basically provides the connectivity between the access to the services and to the content. And as I already mentioned, we need to take the content closer to the end users to provide the lower latency. So we have actually a lot of acronyms on this slide. I will not start opening up. I think in this working group we know many of these, but I agree there's too many of those. But anyway, when we are deploying for low latency, for ultra reliable low latency communications, the user plane functions of the Evolved Packet Core need to be deployed right at the access. In the smallest form factor, it means that they are running in a single server somewhere within the access. And then, depending on the aggregation needs or depending on the requirements, it can be then deployed in the higher latency, more centralized data centers as per needed. But the cloud-native architecture of Evolved Packet Core needs to allow deployment of the workload in various levels in the topology. So that you might have some bare metal proprietary solutions running on router platforms, in terabit router platforms in the central data centers, and then single virtual machine user plane functions at the very edge of the network. So Cloud RAN and virtualized EPC are two of the use cases that are driving. They are definitely not the only ones. So there's a lot on the fixed side, on the cable, on the multi-access edge compute. But in this short slot, it's impossible to go through all of those. So summarizing the open edge data center solution. So we see that the edge cloud is critical. When we are moving towards 5G, we basically cannot avoid building edge cloud capabilities. We need to make it very compact, very easy to manage, very powerful, so utilizing hardware acceleration whenever needed. Hardware acceleration needs to be pluggable. It cannot make the solutions proprietary. So the open architecture needs to enable all of that. And with this kind of architecture, we can also implement, for example, machine learning at the edge of the network, use cases such as, for example, video analytics at sites. You get basically so huge amount of data out of the cameras, out of the video, that it doesn't make sense to transport that to the central data centers. So you need to process it locally. So that's what we want to achieve with the Open Edge project within the Telco working group. And in the next presentations, we will hear more details about the current proposal for the Open Edge architecture and how we can actually collaborate together on that. All right.
So does anyone have any questions?
Yeah, if you have some questions, I'll be happy to take.
I know that this thing doesn't happen overnight. Do you have any idea in terms of the schedule for this possibly like CRAN?
Yeah, on Cloud RAN, things have started already some time ago. They haven't progressed very fast, but there have been some initial, even commercial deployments for Cloud RAN. They started very much from virtualizing the non-real-time parts of the radio, so kind of a layer 2 plus the easier parts. Okay. But now there's more and more interest into virtualizing even the lower layers, the very real-time parts. And I think that's something where we start seeing some field trials, proof concepts more during 2019, and then commercial deployments after that. So it's still in early stage.
Yeah. All right. Thank you.
Okay, I have two questions. So, because I've been looking at the edge. In fact, I was interested in the edge for the last 5 years. And now it looks like there's real business needs. So one of my questions is, do you see doing this edge data analysis without 5G first, or do we need 5G? Because you do need to terminate, for cellular, you need to terminate the data plane or the user plane. And my question, I guess, is, are there other ways besides waiting for 5G to do it now, or it's all proprietary?
5G will definitely accelerate many of the use cases that we see here with network slicing. Things like Industry 4.0 use cases will be much more convenient. But there are definitely things happening also before 5G. So we have Cloud RAN within 4G happening. We have MEC use cases that are not really 5G dependent. So I would say to a certain extent, yes, this can be done without 5G, but it will definitely get a significant boost with the 5G.
Okay. And my second question, this is more practical. So once you deploy, well, I'll just give background. So I'm actually Mark Kiyoshi. I work for Huawei, but I worked for AT&T for 40 years. So there's all these things I had to deal with doing a lot of service deployments. So when you start deploying these edges, I understand the purpose of the edges is you want to have a lot of analytics, right? You want to do real-time analytics, and videos become a big deal. And so now you need these specialized GPUs. You need to deploy all this sophisticated hardware, and of course you're in a constrained space, power, cooling, right? And so my concern is technology evolves very quickly, and our application thirst for power and CPU power and storage never decreases. It always increases. And so the logistics is, how do you deploy day one, and then as the CPU power gets cheaper and faster, and the RAM gets faster and so forth, whatever, memory gets faster and so forth, that it lasts for years versus might only last, I mean, look at our phones. People are buying them almost every year, every other year. And so you have the logistical challenge, even though the vision looks wonderful, but you have the challenge of maybe replacing the hardware every couple of years. Do you see that?
Yeah, I think we are seeing that challenge also on the bigger centralized data centers, because the improvements in power efficiency and also in the processing power, for example, for CPUs are happening every year in such a pace that we are gradually kind of shortening the life cycles in the field. We can support 10-year life cycle for this equipment or this kind of equipment if needed. But it's not something that we would recommend anymore. So it's not like we would necessarily go towards the type of a life cycle that Facebook has, which is probably talking about 36-month lifetime for the equipment and replacing after that. But
yeah, so the logistics of changing at the edge versus a data center. In the data center, you can move traffic over, upgrade and so forth. You're at an edge. You don't have all that. So now you have to do live swapping. I guess you have duality, and then somehow you do the swapping. But that's why I said logistically, this is difficult. No, so has anyone thought?
I agree. I think there's definitely more work replacing those in the edge data center. That's why, for example, automation is so crucial. That when you are doing that kind of renewals, you need to.
Oh yeah, but the truck roll is always expensive, though.
True.
Truck roll. Okay.
It's about the business case.
Yes, I have two questions. In slide 10, you showed the edge base station server attached to the pole. So I was wondering, are you actually thinking about some ruggedized servers can be attached to the pole or outside environment, or are you thinking about standard rack systems, which is a micro data center type, modular data center type form factors or like that? That is first question. And also in slide 12, you showed about open data center management solutions, which can be kind of distributed DCIM kind of software management, remote management solution. So are you actually having that solution in this open software solution, I guess, in this specification and so on? For your information, I'm from Schneider Electric, so yeah.
Yeah, thanks for the question. So if we start from the management piece, so actually the management solution that we have for the OCP-based gear, so it's something that can be adapted for any type of equipment. So as long as we are supporting open interfaces like IPMI or Redfish, it's not the open source software as such. We haven't at least open sourced it yet, but the concepts that are there are basically universal and have been presented actually in the Telco working group also earlier. Then the other question was about the base station. Yeah, so actually the server, the open edge design that we are presenting, it's something that is already ruggedized in that sense that it can handle more wide temperature conditions. And what, like mentioned, on our booth we are showing also outdoor cabinet where you can actually install these as a small data center and even put it running in a pole if you like. But it's basically supporting temperature ranges from -40 to +55. It's IP65 cabinets. If you need more capacity, then of course modular data center, some small container data center type of a module, then is the next step after that.
So I was also interested in, I think Hugo showed one of the use case as being in a CO. I think we're starting to notice not all COs are big, right? And it doesn't make I guess our economics to go deploy a big rack or like a data center type, even though it's one rack. I think it's still we're struggling with the business case. So, meaning, is this something that I think we could also target for like small central offices for fixed access, like the OLTs and more of a disaggregated solution?
Yeah, definitely. So in the central office, we see that often there's a limitation, for example, on the depth of the racks. So it doesn't help that we are cutting open rack to half because it's still 1 meter deep, basically. So we need solutions that are kind of more compact in terms of size. And for example, here we are talking about less than 600 millimeter cabinets, which fit basically to CO very well, and use cases like running OLT here or running software-defined access network or BNGs or CMTS and so on. So they are definitely valid.
And also, have you thought about like, I guess I'm not in the wireless, but then I think they're coming up with the OCPREG, and so I think there is a need to put like a TSN switch closer to the edge. So I think that could probably be another use case that you're looking at. Yeah,
actually the form factor should be such that it allows plug-in units that are having various functions, whether we are talking about general compute or acceleration or doing things like, for example, front hall gateway type of function, which converts OCPREG to traditional CPRI or whatever. So they should be all facilitated by the form factor. It should be open in that sense.
Okay, I look forward for the design.
Very good. Thanks.
Okay. Looks good.
All right. Thank you.